Alright, hello. So we are going to continue with our discussion of Chapter 4 about forces in one dimension, looking at how Newton's laws are used. So far we've discussed Newton's first and second law. So let's review a little bit. So Newton's second law identifies the relationship between the net force that's exerted on an object and the object's acceleration. And we also talked about the relationship with mass. And so this was where, This is where we came up with the relationship force is mass times acceleration. So for a free-falling object, which is what we're going to talk about today, we assume already that there's no air resistance. And this would mean there's nothing touching it because gravity is a field force, not a contact force. So the only force acting on this object is due to gravity. And so we can rearrange the force equals mass times acceleration equation just to involve gravity. So the force due to gravity is equal to the mass of the object times the acceleration due to gravity, which for our purposes here we'll denote with a letter G. So even when an object is not experiencing free fall, we know that gravity still affects it. It acts on everything. It's what keeps you in your chair instead of you floating around. And then, obviously when you go to space, because of that lack of gravity, that's why you're floating around. So gravity is acting on you all the time, even if you're not falling, plummeting to Earth, for whatever reason. Okay, so we know that mass is a part of this relationship. And so let's talk about the difference between mass and weight. So if you took a scale to the moon and you weighed yourself, would your weight be different? And we know that yes, it would be. It'd be less, so we would all want to weigh ourselves on the moon. But will your mass be different on the moon? And the answer to that one is no. Okay, weight is a measure of the force due to gravity acting on you. But mass is a measure of all the particles that make up you. And so the only situation that you could have where your mass would be different on the moon is if on your travel there you had some catastrophic event and lost your leg or something. In that case, probably weighing yourself wouldn't be your priority, but your mass would be different because you've lost some particles. Otherwise, mass is going to be the same no matter what. Weight, because it's due to gravity, is going to change. So force, in the form of gravity, can change, but the number of particles cannot. Okay, so we were talking about weighing ourselves, so let's look at some different examples of how we could get different weights. Okay, so when you stand on a bathroom scale, the scale exerts an upward force on you, and we call this a contact force because you're coming in contact with the scale. But you're just standing there, you're not accelerating, so we would say that your net force is 0. So if the scale's pushing up on you, then we need some other force pushing down on you to create this net force of 0. And so that becomes the force due to gravity, which is your weight. So FSP, which is the spring force, which comes from the scale, has to be equal and opposite to F of G, which is due to gravity, which results in your weight. So the spring scale measures weight, not mass. Okay, the reading on the scale is determined by the amount of force that the springs exert on you, which we know are equal and opposite to the force of gravity pushing down on you. So on the moon, the scale is going to read differently because the force due to gravity on the moon is going to be different. And this is called your apparent weight. So whatever weight that scale gives you is your apparent weight. Okay, so let's look at some different examples of how this works. Okay, so in example 1, let's say that we take our scale and we put it into an elevator. And I wish we could try this here. So the upward force of the scale must be greater than the downward force of your weight. And the reason for that is because you are accelerating in the upward direction. If we're accelerating, we know there must be a net force. Net force can no longer be 0. And if we're accelerating upward, then we know that the upward force must be greater than the downward force. Well, we know that force due to gravity always acts down on you. And so to be accelerating upward, we need a larger spring force or force due to the scale. So the scale reading is going to be greater than your actual weight or the force due to gravity because that's what's going to be shown on the scale. So you would probably not want to weigh yourself going upward in an elevator because it's going to show that your apparent weight, the force of the spring scale or the force on the scale, is going to be greater than the force due to gravity. So you're going to feel heavier. The floor is going to press harder on your feet. You can feel that in those rides that shoot you up and then drop you down, or even if you get in an elevator and it goes up, you can kind of feel you're being pushed on a little bit. Okay, so the second example we're going to look at is if we're accelerating in the downward direction. So now you're going downward in the elevator. In this situation, you're going to feel lighter because the scale has a low reading. So if we look at our free body diagram again, force of gravity is still pushing down on you, and the force of the scale is still pushing up because it's, you're standing on it, it's making contact with you. But because you're going in a downward direction, we know the force due to gravity has to be larger because you do have a net force because you do have acceleration. And so we make a smaller spring force, which means that your apparent weight, which is due to the scale, is going to be lighter or a lower reading than the force due to gravity. So this would be the optimum situation in which to weigh yourself. So the apparent weight is the force an object experiences as a result of all the forces acting on it, and it's what gives the object acceleration. Okay, so you've got your real weight due to force due to gravity, and then the force that the scale reads. Okay, let's look at a third example, which we hope never actually happens, but what if the elevator cable breaks? Now you're going to basically plummet to the ground. So the scale and you would both accelerate, and you would accelerate at the acceleration due to gravity because you're basically in free fall. So this would equal your negative 9.8 meters per second squared. The scale is going to read 0, and your apparent weight is going to be 0 because you're at this free fall. You're going to be considered to be weightless. So weightlessness is when there are no contact forces pushing up on the object, and this is because you and the scale are both accelerating. So the object's apparent weight is going to be 0. Okay, now something else that comes into play here is what's called drag force. And so these are particles in the air that are all around the object that exert forces on the object. And usually, these particles exert a balanced force on all sides, so there really is no net effect. Like in daily life, you wouldn't experience a drag force unless it was really windy or something. Okay, so let's look at an example of that using a suction cup. So we know when you put a suction cup on the window, you push it so that all the air on the inside is removed. So now you've created this unbalance of forces. You don't have a 0 net force anymore. And that's why the suction cup is difficult to remove, because you have this net force of air pushing on the outside, but you don't have anything pushing from the inside. And so that outside force keeps the suction cup adhered to the window. Another example of drag force is when an object is moving through any fluid. And we consider any sort of gas or liquid to be a fluid. So like air or water would be examples of a fluid. So the fluid exerts a drag force on the moving object in the opposite direction of its motion. So if it's really windy outside and you're like running against the wind, you can feel that. If you're trying to run in a swimming pool, you can also feel that it's pulling on you and preventing you from going in the direction you want to go. So this is drag force. It's the force exerted by a fluid on the object moving through the fluid. And drag force is dependent on a lot of variables, including the motion of the object, the properties of the object, its size and shape, and the properties of the fluid that the object is moving through. So if your fluid is more viscous, it's going to be more difficult to move through it, and temperature also affects viscosity, so the temperature of the fluid is going to make a difference as well. Okay, so let's look at an example of a tennis ball and how this relates to drag force. So if I have a tennis ball and I drop it, it's got a small velocity because it has a small drag force. It's a pretty compact object. It's relatively smooth. Not a lot of factors that are going to affect the drag force. So it's falling downward, so that tells us that the downward force of gravity is greater than the upward drag force. Because remember, drag force acts in the direction opposite of motion. And so because the downward force of gravity is greater, this means it's accelerating in the downward direction. So as the ball falls, we know that velocity is increasing because it's accelerating downward. And this also means that the drag force is going to increase because the speed of our object is changing. And so eventually drag force is going to equal the force of gravity so that there's no net force, which means the object will be in equilibrium and there won't be any acceleration. So as our speed increases, our drag force increases, and eventually drag force is going to equal the force to gravity, meaning net force is 0. And we call this terminal velocity. So when our forces equal each other, no acceleration means net force is 0. And this means that we're traveling at a constant velocity. And so we call this velocity when an object's falling terminal velocity. Okay, so terminal velocity is the constant velocity that's reached when drag force equals the force of gravity. Now, this is affected based on the object. So light objects with a really large surface area are greatly affected by drag force, and they will quickly reach terminal velocity. So any sort of parachute or anything like that is very light and a large surface area, and so it allows the person to reach terminal velocity pretty quickly, which is actually a very positive thing. You wouldn't want to keep accelerating all the way to the ground. Heavy, compact objects are not affected as much by drag force. And so if you dropped a rock or something like that, it's not going to reach terminal velocity for a very long time. Okay, so I heard this story on this radio program called Radiolab, and they were talking about cats falling out of buildings. Like in the summer, there were like 150 cats that fell out of these buildings, and they noticed something. They noticed that if the cat fell from 9 stories or higher, that it had very little injuries. They survived, like I think only one out of all the ones that fell from 9 stories or higher survived. They had one that fell from 32 stories and it had very minor injuries, and so all these cats survived. They also noticed that any cats that fell from 5 stories or lower also survived. But it was these cats that fell between 9 and 5 stories that either didn't live or had lots of damage, multiple injuries. And so they're trying to figure out why this occurred. Well, the reason is because of terminal velocity. When cats fell from 9 stories or higher, they reached terminal velocity relatively quickly, which means that they fell at a constant velocity, meaning they could survive the fall when they hit the ground. 5 stories or lower, they weren't falling from very far, and so their velocity when they hit the ground wasn't very large because they hadn't had a lot of time to accelerate. But between 9 to 5 stories, these cats accelerated, and they didn't have enough distance to reach terminal velocity, and so they hit the ground with this high acceleration and didn't survive. So next time you see a cat falling out of a window, maybe decide how many stories it's fallen from and if you need to save her down. But I just thought it was kind of cool that these cats reached terminal velocity. So even though they fell from a higher distance, they still survived. That's kind of neat. Okay, so for some other objects, terminal velocity besides cats, a ping pong ball reaches terminal velocity at 9 meters per second, a basketball at 20 meters per second, and a baseball at 42 meters per second. So again, the baseball being very small and compact. Okay, so we are going to discuss these notes and go over some examples in class. Otherwise, here's the homework that we'll also work on. Have a good day.